Greetings, students. Today, on the 6th of July of 2023, I noticed a nice integral done by Math 505 on his channel, which was the integral from 0 to infinity of the natural log of x plus square root of x squared plus 1 divided by x squared plus 1 dx. And after the substitution and simplifications, he finds another integral to evaluate, which shows that by I1, which is the integral from 0 to pi by 2 of the natural log of 1 plus sine theta d theta. And though I should say that I have learned so much from this person and from the very nice tricks that he does and his interest in Feynman trick, I'm just going to do this integral not necessarily a simpler way, but a different way. And to make things simpler, I'm just going to change theta to 2 theta, and that would change the bound of integration to from 0 to pi by 4. So I get this I1 as the integral from 0 to pi by 4 of the natural log of 1 plus sine of 2 theta. And we also get 2 d theta here, and I'm going to pull that 2 out. And this 1 plus sine of 2 theta, we can write it as sine squared plus cos squared plus 2 sine theta cos theta, which can be factored as sine theta plus cos theta all raised to the 2. And sine theta plus cos theta can be written in the compacted form as the square root of sine of theta plus pi by 4, which you can verify if you use the sum and difference formula of those good old trig identities. So now my integral I1 is, we have a factor of 2 here, and I'm also going to track these 2 down. So we get 4 times the integral from 0 pi by 4 of the natural log of square root of 2 times sine of theta plus pi by 4. And now we can write this as the natural log of square root of 2 plus the natural log of sine of theta plus pi by 4 using log properties. And the value that we get from the integral of just ln of square root of 2 from 0 to pi by 4 is just pi by 4 times ln of square root of 2, and then there's a factor of 4 outside the integral, and if we include them all, we get, there's a 4 and there's a pi by 4 and there's a ln of square root of 2, which we can write as half of natural log of 2, and finally we get pi over 2 times natural log of 2. And then we have 4 times the integral from 0 to pi by 4 of the natural log of sine of theta plus pi by 4. And now I'm going to change theta in this integral to theta minus pi by 4, and it would change the bounds of integration to from pi by 4 to pi by 2, and our I1 becomes pi half of ln of 2 plus 4 times the integral from pi by 4 to pi by 2 of the natural log of sine theta d theta. And for brevity, I'm going to write this as pi half of ln of 2 plus 4 times I2. So now we're gonna focus on I2, which is the integral from pi by 4 to pi by 2 of the natural log of sine theta d theta. And here I'm going to use Euler's formula for sine theta, which is e to the I theta minus e to the negative I theta divided by 2i, which after you multiply the top and bottom by e to the negative I theta, you get 1 minus e to the negative 2i theta divided by 2i e to the negative I theta. So our I2 becomes the integral from pi by 4 to pi by 2 of the natural log of 1 minus e to the negative 2i theta minus the natural log of 2i e to the negative I theta d theta. And since it's clear to us that the result of this integral is going to be a real number, I'm only interested to the real part of these integrals. From this second function though, after using log properties, we get natural log of 2 plus natural log of I minus I theta. And after we integrate, we get something imaginary from these two terms. These two terms are going to give us imaginary results. And the only part from this second integral that gives us something real is this natural log of 2 with a minus sign attached to it and integrated from pi by 4 to pi by 2. So from that we get pi by 4 times the natural log of 2. And then we have plus the real part of this integral, pi by 4 to pi by 2. And here for that ln of 1 minus e to the negative 2i theta, I'm going to use the series expansion of that, which is the sum as n runs from 1 to infinity should have a negative sign, and then e to the negative 2i n theta divided by n, and integrate with respect to theta. Okay, so we get pi by 4 times natural log of 2. I can pull this minus sign out, so we can minus the real part, and I'm going to swap the order of summation and integration, and running from 1 to infinity, we have that 1 over n, and then the integral from pi by 4 to pi by 2 of e to the negative 2i n theta d theta. And this integral will be evaluated very simply as 1 over or negative 1 over 2i n times e to the negative 2i n theta evaluated from pi by 4 to pi by 2. I can write this negative 1 over I as positive I. 1 over I is negative I. If you multiply top and bottom by an I, so negative 1 over I is positive I. And I can pull that out along with the 2 from the series. So this becomes pi by 4 times natural log of 2, and I have minus half of the real part of I times the series as n runs from 1 to infinity. We have a factor of n here, a factor of n there, so that makes n squared. And then we have e to the negative 2i n theta evaluated from pi by 4 to pi by 2. And that is e to the negative I n pi minus e to the negative I n pi over 2. Okay. So here, this e to the negative I n pi, this is just negative 1 to the n. And then use a different color here. This negative e to the negative I n pi over 2, we can write that as negative cosine of n pi over 2. And then there is a negative I, so plus I sine of n pi over 2. Okay, cool. But remember that we are only interested in the real part of this result. But since we have an I here, the only thing that will give us a final real result is this portion. And we have an I there, another I there. They make I squared, which is negative 1, and we can pull it out, and that will turn this negative sign to a positive sign. So finally, we get pi by 4 times the natural log of 2 plus 1 over 2 times the series as n runs from 1 to infinity of sine of n pi over 2 divided by n squared. And if we break this series into odd and even terms, you notice that you get 0 for the even terms and non-zero for the odd terms. So we can write these as pi by 4 natural log of 2 plus 1 over 2 times the series over k as it runs from 0 to infinity. We get sine of 2k plus 1 pi by 2 divided by 2k plus 1 squared. And sine of 2k plus 1 pi by 2 is negative 1 to the k. And you must have noticed already that this nice looking series is nothing but Catalan's constant. So this is pi by 4 times the natural log of 2 plus Catalan divided by 2. Okay, now let's flash back. The integral we evaluated here, this final result is I2, and our I1 is pi half of ln of 2 plus 4 times I2. This is our I1. So we get pi by 2 times the natural log of 2 plus 4 times this expression plus pi times natural log of 2 plus 2 times cat. And I must be missing a negative term somewhere for sure. Okay, it's pi by 2, pi by 4, natural log of 2. Aha, I found it. That ln of 2 comes out with a negative sign, so I should have that negative sign all along the way to this very last result. So 4 times I2, this term becomes negative. So finally we get I1 as negative pi by 2 natural log of 2 plus twice the Catalan's constant. And I think I already verified this result using my Maple software. The integral from 0 to pi by 2 of, that's actually 1 plus sine of x, but they're actually the same. That was also nice to know. And the answer is 2 Catalan minus pi half of ln of 2. 2 Catalan minus pi half of ln of 2. And that's perfect. I hope you liked it. Thanks for watching and have a good one.